Okay, the first thing I want to say about this chapter on nuclear chemistry is getting across the idea that this is a different type of chemistry. When we think about a typical chemical reaction, we have either electron transfer for a redox or maybe a precipitation reaction, and acid-base reaction, all of the combustion reaction, all these reactions we've seen up to this point, the electrons are what are involved in the change. They're either lost and gained or rearranged, or they cause attractive forces to occur, something like that. In this chapter, this is in the nuclear chemistry chapter. What we see is the nucleus actually changes here, and what we can have is the types of change that we're going to see is well, actually, the very last thing that we're going to see on this lecture, the decay reactions, where you take some unstable radioisotope and it falls apart by itself, and in the process it's going to kick off some type of radiation is what we're going to see in one form. Another type of chemistry here is actually a bombardment reaction, where things are slammed together to form a new element. So we're actually changing elements when we start talking about nuclear chemistry here. Now, to set the stage for this conversation, I want to review there's a couple of topics in the first few slides here on Gen Chem 1. The first topic I want to review, isotopic notation. Well, just know that there are two different ways to describe an isotope. This isotopic notation, I'm going to use either one of these. Actually, you might actually see another variation of this. I don't know if our textbook uses it much, but I've seen it in other textbooks where they just use the element's name in front, and then the 12 in all of these labels, and we see it here, is the mass number. And so just remember what this information is telling us. The mass number tells us what all the particles, the number of particles in the nucleus, protons plus neutrons, and then down here, the atomic number tells us what the number of protons are in the nucleus. And since we're dealing with a neutral element, and how do I know that? Well, there's no charge up here. If we're dealing with an ion, that charge is always explicitly written when the ion is by itself, and that's not what we see here. So we know that the number of protons and electrons are equal in these symbols, and that value is given by the number in the lower left-hand corner here. Now notice that up here for these two forms of the isotopic notation, the atomic number would be determined by looking at the periodic table and seeing that carbon is number 6 on the periodic table. And so either one of these three isotopic notations tell you all that you need to know for the given element in the terms of what are the particle counts that make up that particular isotope. And when I say isotope, I guess this is a reminder as well. An isotope is you're dealing with you're going to have the same element, just really the number of neutrons, and that's the symbol for neutrons. The number of neutrons are going to vary from one element to the next. For example, the element carbon, there's two, mainly, I guess it depends on how you count them up, but there's two naturally occurring, I just did that. Two naturally occurring isotopes of carbon. Carbon-12, carbon-13, somewhere around 99% of the carbons on this planet are going to be the carbon-12. Somewhere around 1% is going to make up, is going to be the carbon-13 isotope. And what does that mean? That means that the carbon-13, it has 7 neutrons and 6 protons, and there's the proper notation for protons. that's something else we're going to learn. We're going to learn some new notation for this particular subject. Last time I checked, 7 plus 6 equals 13, so there's my mass number there. Now, I sort of hesitated when I started going into what are the naturally occurring isotopes of carbon. Well, there's another one. There is carbon-14, but it's in a very trace amount, and sometimes you actually don't see that referenced when they start talking about the naturally occurring isotopes for carbon. So, what we have here for these particular elements is, or these particular isotopes, is that we still have carbon. The identity of the element that dictates its chemical properties, if you will, is determined by the number of protons that are in the nucleus. And in all three of these symbols, all three of these isotopes, we have 6 protons. So therefore we have carbon. The only thing that's varying here is the number of neutrons. And what we're going to learn is that, well, that can partly be used to determine, well, do you have a radioisotope, and how is it going to fall apart? What type of radiation is going to kick off when it does disintegrate? Those are some of the other topics that we have in front of us. Let's look at some of these radioisotopes. Now, this is a true statement saying that the carbon-12, carbon-13, and if you like to count carbon-14, it does form on this planet. If you call these, you would say these are the naturally occurring isotopes, and that's a true statement. And notice on this next chart here, oh, they don't have it. Well, notice that they reference synthetic radioisotopes. Well, as it turns out, there is a carbon-11, and it's a synthetic isotope, and it's created. It's man-made. I'm not a nuclear chemist, so I'm not sure exactly the logistics that's required to generate some of these isotopes, but there are a fair number that are significant. That are synthetic radioisotopes, and I guess for us, just looking at a list of radioisotopes, we really can't tell whether the thing is going to be synthetic or not. So I'll just say that right off the top. In terms of predicting radioactivity, well, there are some guidelines that you can use, and we'll see those. But really, I don't expect you to be able to predict yes or no whether something's radioactive, at least in some exact way. So just know that. What I want you to know, one thing, is that nuclei with at 84, this is on the periodic table, atomic number, i.e. the number of protons of 84 or more, they're all radioactive. It doesn't matter which isotope you're looking at. There's not a single stable isotope that has 84 or more protons in the nucleus. It just doesn't happen. There seems to be, again, I'm not I'm not a nuclear chemist, but there seems to be, some finite size that the nucleus is still stable at. It's almost like as you pack in more and more particles into that nucleus, it just becomes a more stable, unstable arrangement. Part of that is the fact that, well, what are protons? Protons are positively charged spheres, and the last time I checked, when you start bringing two things that have the same charge to one another, there's a repulsive force. Now what happens in the nucleus actually is that there's a strong and weak nuclear force. It's a strong nuclear force that actually keeps the nucleus together, and that strong nuclear force is stronger than the repulsive coulombic force for a stable radioisotope. Or I should say a stable isotope. Therefore, it's not going to disintegrate on you and kick off some kind of radiation. But there seems to be some point, we see 84 protons, where the repulsive force is essentially is starting to become a much more of of an issue, and it can't be negated as by the strong nuclear force that's felt in the nucleus by the protons. And then something else is happening in terms of radioisotope stability. If you can squeeze in a lot of neutrons, if there's a high neutron to proton ratio, and we'll talk about this later on, that tends to stabilize the structure as well. I almost visualize it as the neutrons sort of shielding the Coulombic repulsive force between the protons and the nucleus. Is how I've always pictured it. Again, since I'm not a nuclear chemist, I can't speak exactly what's going on, but that's sort of my naive take on what's happening inside the nucleus of an atom. And again, we'll look at the stability thing a little bit more closely here in a few minutes. A couple other things on this chart that we will deal with. The half-life, we've dealt with half-life before. Back in chapter 14 in the chemical kinetics chapter. And we're going to come back to nuclear kinetics here. And it's still, what we're going to see is that the decay process that we're going to describe here, and this talk about half-life, they're all first order reactions. So we'll revisit that particular equation in the second presentation for this chapter. But notice that the half-life here, and remember, if I start off with 1 gram of this particular isotope of uranium, I'm going to have to wait 4 billion years before half of that uranium has disintegrated, and then I would have to wait another 4 billion years for half of that sample to disintegrate, and so on and so on. Why is a nuclear power plant such a hassle? Well, beyond the possibility of Chernobyl kind of event, which is much less likely in the Western world, there's this issue of who's going to be around 4 billion years from now, or the plutonium 10,000 years from now, to look after this extremely dangerous radioactive substance. So, that's something to consider for the issue with the waste from a nuclear power plant. So we'll talk a little bit about the half-life, but they're not all that long. You can see that some of them are very short, actually. So, the thing I want to talk about in this particular presentation is more along the lines of the stability of the radioisotopes and the type of decay that you're going to see. So what are these, alpha and beta? What does that mean? Well, let's look at that here in a minute. But just know that these are not the only two types of decay pathways that we're going to talk about. And when I say decay pathways, I mean that disintegration of the uranium isotope to something else. Well, it's going to form another it's probably going to form another radioisotope, and then it's going to kick off some kind of radiation. And this type of decay is telling us the type of radiation. So beta radiation and alpha radiation are two types that we're going to see in this chapter. Now this slide is actually it's from chapter 2, the types of radiation. I think it's a pretty good slide in terms of describing some of the at least physical properties of the different types of radiation that we saw back in Gen Chem 1. So they have some kind of radioactive source. There's a pinhole in this plate here, and what we do is we just get a stream of radiation passing through these electrical plates. And one thing to notice is that you can, what is this diagram telling us? Well, these things called beta rays are deflected toward the positive charge plate here, and so that tells us that right down here that we have an overall negative charge on the beta particle or beta radiation. Down here, the deflection of the alpha ray is toward the negatively charged place. So what do we know? What do we see? Is that it's a overall positive charge. Now, and to put a finer edge on it, what we have in front of us, we have a helium nucleus for the alpha particle, and then we have a high energy electron for the beta particle. And then the last one, the gamma ray, it's just a type of light, a type of photon. It's a high energy electromagnetic radiation, EMR. So it has has a higher frequency than visible light, a shorter wavelength than visible light, and as a result, it's pretty dangerous too. And notice when it passes through the electrically charged plates, there's no deflection whatsoever. So, I mean, just like a photon, there's no charge on the thing. Last thing I want to say about this is just notice the magnitude of the deflection. It's actually telling you something about the mass. The alpha particle, it's like throwing a bowling ball through here, something nice and heavy. It's not as it takes more energy to deflect it. So, if you have a certain force that's being applied across this electric field, a constant force, then a big, fat, heavy bowling ball isn't deflected as much as something like a ping pong, where it would be deflected to a greater extent. So what it's telling us is that the beta particle is much lighter, which, I mean, we know that. We can actually see the value here, 10 to the minus 8 versus, or 10 to the minus 28 versus 10 to the minus 24. So it's much heavier, and that's actually one of the things. I'm not going to ask you to memorize this exact number, of course. I don't do that, but you should know that this is a really heavy, as like like radiation goes, if you're talking about a nucleus or a particle, this is a really heavy fat particle, and this is a very lightweight particle, and you should keep that in mind because we are going to talk a little bit, I think, in the second presentation about the relative penetrating power for these different substances. And notice that 1 means very low, 10,000 means very high. That means that if you want to stop a gamma ray from passing through you, you need to be standing in front of 6 to 12 inches of concrete. Versus a alpha particle, it's big and fat. As it slams into the concrete, it's just not going to penetrate very far. So we'll see a little bit of that issue in not calculating anything, just sort of a conceptual sense in the second lecture. Now, these are not the only types of radiation that we have to worry about. There's a few others in here, and let me. I'm going to circle the symbols that I will be using, those guys. So we have a few other things to worry about. I mean, we've already dealt with, in one form or the other, these 5. And I guess actually, the electron will be talked about in some of these examples, so I'll leave that up there. But notice the symbol for the electron and the beta particle are the same. The phrase that's used for beta particle is a high energy electron, and so it's just got a little bit more kinetic oomph, if you will, than electron. Electron would be reserved for this chapter is something in the one of the atomic orbitals close to the nucleus, and we'll see that in at least one example today. And we will be using these, even though that we've only talked about alpha, beta, and gamma radiation, we do see all these other symbols playing a role in terms of, well, what can physically happen to a radioisotope, and also what can what are some of the conceptual leaps that we have to make in terms of accounting for the changes that we see. And we use these symbols quite a bit. So just go ahead and pencil these into your little book of things to know. The other thing, the new one on here is a positron, and all it is it's an electron with a positive charge is essentially what you're looking at for a positron, and we will be using that for there'll be what's called a positron emission process that we'll take a look at, where a radioisotope can decay and then kick off a positron. Why does a radioactive substance do what it does? Well, it's trying to gain some kind of stability, and that's what we see on this particular chart. two things that pop into my mind when I see this this slide here is one. This on a problem. I'm going to give you this chart actually. I want you to be able to. I don't want you to memorize this chart. I want you to be able to interpret the chart. I want you to be able to use the chart in terms of predicting what's going to happen to a particular radioisotope. If I jump forward a few slides to one of these problems, notice the use of the stability chart. I want you to be able to look at the chart and predict what kind of decay is going to happen for a given isotope. And there's some guidelines that we go by here to figure that out. So I'll give this to you. And then also, if you need the magic numbers, I'm going to give that to you as well. So don't worry about, if you're very good at memorization, terrific. Go ahead and you can pencil those in as well. But it's not like I'm going to say, what are the magic numbers for protons? You're not going to see that. But what this is here is telling us that there are certain properties of isotopes that tend to cause the isotope to be stable. Is what we're looking at here. You know, what causes the isotope to be stable? Well, one observation that's made is that there are such things called as magic numbers, and you see this in any textbook. If a particular isotope has a proton count of 2, 8, 20, any of these numbers, it tends to be more stable. It doesn't mean, I think, again, I'm not a nuclear chemist, but I can only imagine that there are definitely exceptions to all of these rules. So keep that in mind. But there does tend to be a trend in these particular, these numbers tend to lend themselves to stability. If you have a count of neutrons of one of these magic numbers, and notice that 126 is thrown in there as well, then the isotope tends to be more stable than usual. We'll put it that way. Now, what's the physical reason for this? Honestly, I don't know. So that's why I'm not going to emphasize it on too much. I like to emphasize things that we can use our logic in terms of answering a particular problem. For example, you know, if we have an even number of protons and neutrons in the nucleus, that tends to be more stable. And then also, if we have a high neutron to proton ratio, we tend to have a more stable isotope as well. And that's what the stability chart is showing us. So what we have here, we have the neutrons over here, and that's I'm gonna try to use those symbols as much as I can to get you used to it. And then the number of protons down here. And then notice that, you know, if that ratio is 1 to 1, then it's just this line, this linear function going up the graph is what we see here. And down low, well, that's about 20 or so. That 20 is calcium on the periodic table. So, you know, from calcium or below, what we see is there's well, a lot of the radioisotopes is stable, which doesn't shock us. You know, smaller nucleus just tends to be more stable. And then, you know, if the ratio is 1 to 1 between the neutrons and protons, then it tends to be in this band of stability, which is, there it is, belt of stability, as you go up the periodic table, or go up this particular chart. And I guess we are going up the periodic table. We're increasing the number of protons here. Notice that it maxes out at 80, because remember, 84 or above, this chart is just going to keep extending up on that same trajectory pretty much. But 84 above, we know that they're all radioisotopes. So some may be more stable than not, but they're all going to disintegrate at some point or another. So what we can use is just whatever I talk about for mercury here, this 1.5 to 1 ratio that I'll calculate here in a second. It's just that band just keeps extending up in the same slope, if you will. Okay. But what is it telling us is that so each one of these little dots represents a particular or a particular isotope for that particular element that is determined by the number of protons here. So you can see that atomic number 50, which is let's see, that is 10. So 50. Let's just go and label that. That's the metal 10. Notice that each little dot represents it'll be a fairly stable. Oh, there's SN right there. A fairly stable isotope in there, and there's quite a few isotopes for 10. And whether it's synthetic or naturally occurring radioisotope, it really doesn't matter at this point. We treat them all the same in terms of our analysis here. And as it turns out, for 10, if that ratio between the neutrons and protons is 1.4 to 1, then it tends to be a fairly stable isotope. So just a little comment about how this ratio is determined. Let me rewrite that's 120 and 50. That particular isotope for 10 there. Well, the ratio between neutrons and protons, which is what they're talking about here. Well, there's 50 protons in there. There are 70 neutrons. How do I know that? Well, 120 represents the total number of neutrons and protons. So if I remove that number of protons, then I have 70. 120 minus 50 is 70. And then if I divide 70 by 50, what I get is that 1.4 to 1 ratio. And so, if you have really, and not just for 10, but any of its neighbors as well, there's some range in here where this is going to work pretty well, then this is a fairly stable isotope. If it does decay, if it does fall apart, it's typically going to track that way. It's going to stay within the band of stability, because that's what all radioisotopes are trying to get to, is this band of stability. If they're way out here on the chart, then they decay a certain way to make it back to the band of stability. If they're way down here, they're going to decay in such a way to back up and go up towards this band of stability. If they're within the band of stability, then they try to stay in the band of stability. And actually, the rule of thumb that we're going to use is that, for example, to stay within that band, is that it would undergo this loss of 42He. That's an alpha particle here. And so, using this little, and we'll go back to this guy, to stay within notice the number of neutrons, number of protons, it's just sort of a zoomed in picture of that same chart that we looked at. And to stay along that vertical stretch of the band of stability, then it's typically going to undergo some kind of alpha decay process. And so my best guess is that if 10120 is a radioisotope, if it disintegrates, then it's going to kick off an alpha particle. Okay, so and we'll look at these equations here in a little bit, and then notice that as you get closer and closer to 0 down here, or hydrogen to 1, then that ratio changes. It's about 1.25 to 1 for the zirconium, and then for mercury, as you get up high here, it's a 1.5 to 1 ratio to this band of stability. So there's you can see here, 1 to 1 is drawn on the line here, and then there's a slow, there's some kind of arc that's occurring, some kind of bend in the band of stability there, away from this 1 to 1 ratio, and you see it here, the 1.5 to 1 ratio for these different radioisotopes. And the 1.5 to 1 ratio, we'll just go ahead and use that for the other ones that's beyond this chart. Okay, I mean, it's not, there's a little bit of a zigzag it gets up there, but I'm not teaching, I'm not expecting a lot of nuclear chemist out of you guys. So I just want to expose you to the chart and the concepts here, and give you a little bit of some level of comfort when you're looking at this particular subject. Now, the first thing we should do, we've talked so much about it, let's actually just sort of use our guidelines here in terms of figuring out whether or not something is, you might expect it to be stable or not. Actually, the tin here and the lead, notice that the number of neutrons here, if we go back to our chart here, this is actually 50 and 82 for protons. It's a magic number. And so what we see here is that these two are, just by looking at that number, suggesting they're probably more stable than not. And again, I'm not going to have you memorize the numbers. I would actually give you the magic numbers if I want you to use them. But you will have the that chart showing the band of stability, and so and then the other two bullets on this list, the even number of protons and neutrons and the high neutron to proton ratio. You should be able to use those kind of information in conjunction with the chart here to predict the stability of these guys. And if you remember the magic numbers, that's great. Let me just quickly lay this out here. 68, 125, 85, 126, 82, and that corresponds to the neutron-proton ratio for all of these guys. Well, I mean, one thing I'm seeing is that, again, the two that had the magic numbers to begin with, they also have an even number of protons and neutrons, and that's one of the criteria that we looked at on that last slide. And then if I want to calculate the ratio here, I don't know really. Let's just see what it comes up with. That's about 1.36 to 1. This one's 1.47 to 1. And then that last one is a 1.54 to 1. Now, one thing I want to say is that the ratio here, it's useful. The next example is where it's probably more useful for us in terms of predicting the kind of decay pathway that's going to occur for a particular radioisotope. I'm not so worried about it here, but let's just use it anyway. Well, we already saw 10 on that last example. It was 1.4 to 1 for 10, which was stable, and that's okay too. So my guess is that this 1050 is a fairly stable isotope. It may be completely stable. Matter of fact, I would tell you the truth, I would have to look it up in the book to be certain about it. Just because honestly, I'm not that familiar with some of the nitty-gritty detail of radioactive isotopes. And then the lead over here, let's just actually lead 82. In some ways, I don't need to look at the chart actually, because I know it ends at 80. So again, I said anything that was above that, we just assume if it's 1.5 to 1, then it's going to be a fairly stable radioisotope. So it's a little high actually, but I'm going to say it's okay anyway. And then actually this one's a little low. This one's even higher up on the chart, and it's falling away from the 1.5 to ratio. So I would say that this AT isotope is probably the one that is very unstable, and then these two are fairly stable. Okay. The other way, and this is important, this is actually more involved than that last one, is to predict the mode of decay. Now what I mean by that, and I referenced it for the 120 back here, is that when this thing disintegrates, what is the radiation that's going to be when it gets kicked off? And remember, there's quite a few different types of radiation that we can talk about. And I guess those are the big three: positron emission, beta particle, alpha particle. Yeah, when you talk about it being it's emitting radiation, it's those three that typically what you see. When we look at bombardment reactions, the neutron and proton play a larger role, and then there is a mode called electron capture that we will see, and we'll use this particular notation for it. That's where an electron falls into the nucleus from one of the atomic orbitals close to the nucleus, and then the element actually changes. That's the way that the radioisotope can gain stability. So let's analyze this guy and see what we come up with for each of these. So polonium is PO, and it has the atomic number of 84, and its mass number is 120. What I would suggest is to start off doing the neutron to proton to ratio and see what that's telling you, because that's really what's going to be most useful for us, I believe. And for this example, let's see, we have a proton count of 84. It's right there, and then 210 minus 84 is 126, and then if I divide 126 by 84, I guess actually what I'm doing is dividing both sides by 84 to get this ratio. 84 divided by 84 is 1, and then 126 divided by 84 is 1.5. So actually, if we think about this in the context of that stability chart on the 2 slides ago, it has an atomic number of 84, has this particular ratio. Well, that's right in line with that example of mercury that they left off with up here. And like I said, we'll just use that 1.5 to 1 ratio for the rest of the band stability above where the chart gets cut off here. So, what it's telling me, it is 84 above. We know it's radioactive, so it's going to disintegrate. And what it's going to want to do is stay within the band of stability. And like the next chart is showing us, to stay within, this is how it's going to stay within the band of stability. It's going to lose alpha particles. So it's an alpha decay process. Now all the book is asking for is, label alpha decay or beta decay, positron emission, something like that, and then go on to the next problem. Well, actually, I want to show you how to write these equations, because this is the other thing that's important for this chapter. And the dry lab that you will do or you are doing now is sort of helping to reinforce that as well. There's a few of the equations that you have to do for that lab. So these problems are showing up on the dry lab as well. So it might be helpful here. When you're talking about a radioactive decay, all you have a radioisotope, and it just falls apart, and it just kicks off whatever particle you're either given or you're predicting here. I'm predicting alpha decay process, which is true. That is what happens. Remember, it wants to stay within that band of stability. And then the question is, what is the isotope that is formed during this process? Well, when you balance these decay reactions or bombardment reactions, occasionally you see molar coefficients changing, but to tell you the truth, what in large part is just these isotopic numbers, the mass number and the atomic number that you have to worry about. For example, what number plus 2 equals 84? Well, that's 82. What is 82 telling us? 82 is establishing that we are generating a lead isotope. Okay? And then, what is the mass number up here? Well, what number plus 4 equals 210? Well, that's simply 206. Now, typically, I find students are fairly comfortable doing this once they're. That's why I went through that isotopic notation sort of review for you, so you can understand what these numbers are telling you. Once you're comfortable with the notation, you can see the math isn't terribly challenging. It's just a matter of keeping your wits about you about what information is being conveyed by these symbols. And as it turns out, this is a stable isotope for lead. I don't think it's radioactive at all, actually. I could be mistaken, but I'm pretty sure it's not radioactive. So when polonium decays, kicks off the alpha particle, then it forms a stable radioisotope and it stops decaying at that point. Let's look at the other one. Let's look at B, indium. It has, of course, the mass number of 120 and then the atomic number of 49. And I'll just go ahead and tell you, for these large elements that we haven't used them at this point, I'll give you the symbol in case you're uncertain about it. So don't worry about that. I would give you the indium is In, and then, well, you should be able to look on the periodic table and figure out what that mass number is. So, and I'll give you this part going to In anyway, and you can do the rest. You should be able to do the rest. Let's see. The proton count is 49, which actually, that's a red flag right there, actually. I mean, we know this is unstable because it's telling us that it does undergo some kind of radioactive decay. But and then there's 71 for the number of neutrons. This is an unstable radioisotope. You have the count for neutrons and protons are both odd numbers, which tends to form more unstable isotopes. And if we do this calculation, it's 1.45 to 1 is the ratio. Let's look on, this is actually, so 49 is our atomic number. If we look back here at the chart, that's actually in line with the 10 that we looked at a few minutes ago. Now, remember what the band of stability is telling us. Not just that 10 is 1.4 to 1, but really any neighbor of 10 wants to get to 1.4 to 1. Well, the 1.45 to 1 is a little bit high. If we look at this chart here, that we're high on the high end of that band of stability, and this, I marked it out, but that's a beta particle. That's what we have here. So this indium is going to undergo a decay process where it kicks off a beta particle. So that would be, you would say it's a beta decay process, and that is true. And then you would want to go in and show me the decay equation, or the beta emission process. So beta decay or beta emitter. These two terms, when I talk about this, I use these two terms interchangeably. So just look alive when I start using those phrases in class. Now the symbol for the beta particle is that. E for the electron, -1 charge here. It's the way I always remember it. This symbol is actually describing what's happening in the nucleus, and I'll talk about that here in a second. And then the question here is what is in the box, and just like before, what number minus 1 equals 49? Well, that's 50. And we already saw on the previous example that that's the element 10. And then what number plus 0 equals 120? Well, what do you know? That's 120. And so we established what the other isotope is here. And that's probably a stable isotope. Even numbers, there's a greater number of neutrons, so it's probably just fine. And it's right in the band of stability as well. It's that last one that we looked at. These are the two most common types of radioactive decay processes. Magnesium-22 illustrates something that's a little bit different, and I'm going to use that symbol there. If I want to do neutron and proton, let's see, this thing will be 12 and then 10 for the number of neutrons. So that's, well, one problem is that there's a greater number of protons than neutrons. That's, remember, those neutrons are sort of in there to buffer the repulsive force between protons. So if you have a deficiency in the number of neutrons, that's a bit of a problem. And then the ratio is 0.6 to 1. So again, we're dropping the number of neutrons, so we should expect this ratio to start shifting down. And again, you divide by 12. You divide by the number of protons on both numbers to figure out that ratio. And magnesium, if we look at that band of stability, magnesium, so atomic number 12, it's actually in that range. It's essentially a 1-to-1 ratio is where it's stable. Remember, like I said, somewhere around 20 or so is sort of where I cut off this chart in terms of the 1-to-1 ratio. Anything below calcium If it has a 1-to-1 ratio, then you can treat it as fairly stable. And if it is radioactive, it's going to be a beta decay. It's going to drop that way. Well, since it does have a lower, what do we want to do? We want to try to increase that number. We want to increase the number of neutrons in the nucleus. That will cause it to be more stable. Well, the way we do that, we're down here now. We're below the band of stability, and we want to shift back up toward the band of stability. The way that is done is by two processes, and I want you to show both of them. Loss of an electron. Loss of a positron. Notice there's no negative charge there. So that's a positron. And then electron capture is the other option. Let me sketch these out for magnesium. So one, again, it's a positron emission that can occur. That is a +1 there, an electron. What is in the box? And then the other one is the electron capture. And that would simply mean that, one electron, what happens is that this one electron is falling in to the nucleus somewhere, from one of those atomic orbitals close to the nucleus. And in that process, there's actually a conversion. You can see it in the numbers here. 12 minus 1 equals 11. That's the element sodium. 22 plus 0 is still 22. So what we see here is that we're decreasing. Here we have neutron count at 10, and then we have a proton count of 12. And at the end, we have an equal number of protons and neutrons. So during this electron capture process, we're actually increasing the number of neutrons by 1 and decreasing by the decreasing number of protons by 1. Up here, if it kicked off a positron, it's the same kind of process. This would be 11 plus 1 equals 12, and notice that we're going to come to the same isotope. These two are the same thing. And so that's why it says on that chart here that either loss of a positron or electron capture can do the same thing in terms of shifting it back up toward the band of stability. And then once we do that, then we see that, well, now the ratio is a 1-to-1 ratio, which is what we want for those smaller isotopes here. Physically, what's happening with this positron emission, so the problem will be over at this point, but I want to use these examples to inform you a little bit more about what's physically going on in the nucleus. And I want to do this in red. Actually, that should be a 1 and 1. So what's happening so this is a positron emission. What's happening here is that there's a disintegration of one proton within the nucleus, and this is something I want you to know. I want you to be able to reason through this particular process. What happens is that it kicks off. That's where the positron is actually originating from, is from that one proton. And when that happens, what you get is a neutron. And notice that the 1 plus 0, 0 plus 1 equals the 1s up here. So you still have a balanced nuclear equation, and you're accounting for the changes that are actually occurring within the nucleus. So that positron, it gets kicked off into wherever, away from the nucleus, and then this neutron stays within the nucleus. And that's how, the mass number is not changing. 22 goes to 22 because the 22, remember it's protons plus neutrons. So if one proton switches over to a neutron, you don't get a change in the mass number any, but you do see a change in the number of protons there. You drop it by 1. So that's what's going on with the positron emission. Again, physically what's occurring in the nucleus. And then for the beta emission, what's happening? Well, it's essentially the reverse process in some sense, where we're increasing the number of protons, going to 49 to 50. So we're actually going to form a proton when this happens, and it's coming from a neutron. So when a neutron falls apart here and it changes, it kicks off a beta particle, and you're left with a a proton in the nucleus. And again, if you add up the numbers here, like we've been doing for all these nuclear equations, it's an agreement. -1 and +1 equals 0. 0 plus 1 equals 1. And so we're showing the transformation of the particles in the nucleus when a beta emission is occurring. And so I just want to sort of give you a little bit of a foundation in terms of physically what's occurring within the nucleus. Now, these problems that we've been doing with that chart is, well, that I guess in the grand scheme of things, in terms of radioactive decay reactions, these are the most complicated ones, where I'm giving you an isotope and I'm wanting you to go through the full treatment in terms of looking at the neutron to proton ratio, and then looking at the band of stability and trying to predict what's going to happen. So remember, I'll give you this chart, but I'm not giving you this chart. Okay, you have to remember that to go high into the band of stability, it's going to be a beta emission. To go low and back up into the band of stability or belt of stability, you're going to have a positron emission or electron capture, and then to drop within the band of stability, it's going to be an alpha particle. It's going to be kicked off. You need to know this chart and how to use it in conjunction with that guy there. Okay. Now, the other type of decay reactions that I want you to do is to be able to interpret the text that we have here. So we have, what element, that's the reactant, is undergoing an alpha decay. So we have one of the products there, and then the 208 is the other product. And lead is 82 Pb. And our, what's in the box? What element just fell apart here? Well, 2 plus 82 is 84, and that is polonium. And then 208 plus 4 is 212. So it's polonium 212 that underwent that particular disintegration. And then on the same line, it's something like this: balanced nuclear equation. Oxygen 15 undergoes positron emission. So it's telling me the oxygen 15 is actually the reactant here, and it undergoes positron emission. Remembering it's a +1 here for it's an electron with a positive charge. And then what is that stable isotope at the end? Well, what number plus 1 equals 8? That's 7. That establishes nitrogen by just looking at the periodic table, and then 15 plus 0 is 15. So the mass number isn't changing during this process. Okay, so that's a nice introduction on radioactivity. The next presentation will actually look at some kinetics. There's a little bit of math and a little bit of concepts in each of the next two videos coming up, and that'll do it. Okay, thanks.